So this is just a example of the HPLC digital mimic that we've designed. This particular digital mimic we have designed to allow students to prepare solutions, but to have those solutions can be prepared with two different components, which in this spreadsheet is compound X and compound Y. In our normal analysis, compound X is methylparaben and compound Y is lidocaine. But this is a spreadsheet with some of those details removed. So to start off with, the students are faced with a drop-down menu whereby they can prepare a solution. They can choose their weight from a drop-down list. So in this example, I have 47.6, and for compound Y, I have chosen 97.90. The students have an option to choose whatever standard flask size they like. So it may well be that these two compounds have different solubilities, and so there might be different standard flasks required. And the students can change the name. So I'm going to call that standard X, and I'll call the other one standard Y. So students now have the option to move on to preparing their diluted solutions. So here they need, I'll just expand that up a little bit. They need the name of a stock solution. So the stock solution, in this case, would be standard X. Now in these top 4 boxes here, which I've got, I can only have one compound. So I can only use one of the standard solutions that I've generated to create these solutions. And I'll make the other one standard Y. And I'll do a 1 in 10 dilution for them both. So that would be standard X1 and standard Y. Now, I'm actually not going to use these other solutions, so these other 1 compound dilutions, so I'm just going to leave those as blank there. So the next option that I have at the bottom here is to create a combination solution. So I've got good combination A, combination B, combination C, and so on. So in this case, I have an option to combine 2 different solutions into the same standard flask. So I think in this case, what I'll do is I'll combine standard X and standard Y directly. And I'll do that 10 in 25. I think I'll do a 10 in 100. So standard X and Y. And I think in this case, what I will do is I will just have a dilution here of, I think I'll take standard X and standard Y. I'm going to leave this one blank, actually. I'm going to take standard X and standard Y, and I'm just going to make a 1 in 10 dilution of it. I'm going to call that del X and Y. So in this case, what I have done is, rather than combining the 2 solutions into one, I have combined my combination solution and a blank. So it's effectively perhaps only doing it once. Okay, and that's fine. What I am going to do, actually, I said that I was going to leave these blank. I'm not going to, because I would like to have a really dilute solution to see if I could identify the retention time of standard X and standard Y properly. So I'll do another 1 in 10. I'll call that standard X2. And this drop-down menu, I'll call that standard Y2. You can see in this spreadsheet that the students who are using this, who are devising their stocks and their dilutions and their solutions in this spreadsheet don't get to see what the concentrations, what the resultant concentrations would be. Those values are in this sheet, but they are hidden. And the reason that we've done that is because when a student is really doing an experiment in the lab, they don't, the concentration of the solution in the standard flask doesn't magically appear on the side. So I have my different solutions here. I've got standard X1, standard Y1, standard X2, standard Y2, standard X and Y, and a diluted standard of X and Y. The students would now go to this HPLC sheet. And first of all, on the HPLC sheet, on the file name, we have a drop-down menu of all of the solutions that we've created, as well as some of the default values as well. I would like to have a solution that uses both of my that has both X and Y in it. So I'm going to select standard XY. Okay, so I'm actually get quite a nice HPLC trace here. I'll maybe take the intensity of that down a little bit, and I'll try the diluted X and Y. So one of the reasons that I've swapped over to the diluted X and Y is that I want to demonstrate what this replicate function does. That is because I want to demonstrate the fact that the noise level shifts every time we select a different replicate, which is what you would expect if you were running an HPLC experiment. If you did a number of different replicates, you wouldn't always see the same baseline noise. So the baseline noise shifts according to the replicate. In this particular setup, and if you are administering these sheets are available on the blog under a Creative Commons agreement. So you can actually change some of the trace generation parameters to suit yourself and whatever molecules you may be working with. So if I want to, I could maybe start increasing the methanol percentage in the mobile phase. And students can do that obviously without going to an HPLC, and they can maybe, let's just start dropping that a little bit more. And what happens if I change the flow rate to 1 ml/min? Oh, it's not really going to work. Maybe I'll take the methanol concentration back up again. And so the idea is that students have an opportunity to look at the impact of methanol in their mobile phase and the impact of the flow rate as well, without actually going to the HPLC. In our experiments, we would very often ask students perhaps to use a simulation like this to maybe do a linearity test or a linearity validation, or to inject 6 replicates and determine what the mean and the percent RSD, the relative standard deviation on those 6 injections would be. But we also ask students to perhaps monitor resolution values and also asymmetry as well. And this is where this orange line comes in. Now, the orange line is controlled by the integrated start and finish buttons, and we ask students to do the integration of their peaks. Where you can see that we give them the peak area and then the peak maximum and the front and rear width heights. So you can see that I've had to sort of change the values slightly there because I think it just needs to match up. There's 2, oops, yeah, that's right. I just needed to get a proper integration. So we have the peak area, the peak maximum in absorbance. The peak maximum retention time. So, and if I change my replicates, you can see possibly that retention time might shift. So that retention time shifts ever so slightly, as you would see in a real HPLC. We have the peak width at half height, and we also measure the rear width to 10% height and the front width to 10% height, and we ask our students to calculate the asymmetry ratio from that. This is just an introduction on how to use this HPLC digital mimic. If you do go to the blog, there's a full description of all of the hidden cells and functions. I'll actually just show you the hidden cells and functions on this sheet. All of the processing information is described in the blog as well. Just one final thing about the solution preparation. It's actually set up in such a way, I'll reveal these hidden cells as well. This is a randomizer, so this is a selection process which is based upon grade A glassware and some of the volume differences that you would actually see in grade A glassware. So the idea is that students are introduced to the concept that a 10 ml pipette is not 10.000 mils. In this case, it's actually 9.9736 mils. But again, students don't see that information because that would not be the kind of information that you would see in the laboratory. And the idea of the principle here is that students can prepare their own solutions in this simulator, effectively run the HPLC trace, and they have an opportunity to do linearity experiments or repeatability experiments. I will just show how this detector can saturate. We've actually built non-linearities into this as well. So that's going back down. Let me see if I can go back up. And I think if I go to my standard solution. So yes, you can see here that we've actually built a linearity function into the HPLC absorbance, so that if students didn't prepare the correct solutions for the linearity experiments, then they would actually see the normal curves that we would see if they'd exceeded the dynamic range of the detector. So all of the information about this spreadsheet is on the blog, as I've suggested. We've distributed these under a Creative Commons license. So you're free to take them, use them, adapt them. I think we've asked for attribution, but if you could let us know whether you've found them useful, that would be fantastic. Thanks for your time.